This is kind of a cool question. For example, number 3, it says that we want to find the volume of a drilled sphere. And so what we're going to do is we're going to take a sphere, any random sphere, with a radius large r. Okay, and then what we're going to do is we are going to move the inner radius. So large r is the outer radius. That'll stay fixed for the sphere. The inner radius is what will move. And what we're going to end up generating here is some kind of sphere such that it's cut out. Okay, so we've drilled a hole. Watch as I revolve around it. We've drilled a hole right through the center of that sphere. And that center, we are going to make it so that we can vary the size of that center hole just like this. Okay, and of course we can change the x values. Now you can't see those in here, but that's going to do these different spheres. So these different cylinders. So the idea is this. It's pretty cool. Again, we're going to go ahead and we're going to take this thing. And we're going to drill a hole of any size we want to through the center. Okay. Now what's cool about this problem is that we're not actually specifying what size the original radius is and what size the small radius is. So here's how it's going to work. What we need to do is we need to define a circle. I'm going to come up with these right here for you, but I'm going to define a circle of radius large r. Okay, so let me go ahead and draw that guy out for you here. So what I'm going to do is I'm going to create half of a circle over here, so it's symmetric along this x-axis, like this. Okay, and what we're going to do is we're going to rotate that guy around, and that'll give us our sphere. So I'm going to come out with my circle like this. Okay, pretend it's the same. Okay, now I don't know how large this circle is. Now if I took this guy and I just rotated it around, okay, I would get a sphere, right? If I rotate it around this axis. But what I'm going to do here is I'm going to come up with the equation that represents this guy and the separate equation that represents this guy. So I know that my sphere has got to come out a radius of large r. Okay, so we're just going to get the sphere first. Let me get the general equation for this line and this line. So if it comes out r here, it's also got to come up r here. And now the general formula, and this is the y-axis, the general formula for a sphere, well, for a circle, excuse me, is x squared plus y squared is equal to the radius squared. Well, the radius here is large r, so I get this. So this line right here can be generated by solving for y. So it'll be y squared is equal to r squared minus x squared, like that. And now when you take the square root, you got to do plus or minus, so it generates two equations. So equation 1 I'll call f of x, and that'll be the positive one. So that'll be large r squared minus x squared. This f of x will be this top piece. This bottom piece we'll call g of x. And so g of x is the negative version of this guy. So r squared minus x squared, like that. So let's go to Desmos here. And I'm going to type in y is equal to the square root of, now I'm going to make r. It's interesting that it is giving me a value for r and not a slider. That's all right. Let's say r, for example, was 5. So it would be 25 minus x squared. What I want you to notice is that's going to generate this circle here, okay, where it's the top half of the circle where the radius is 5. If I change this to any other number, like 4 squared, like that, I get that. And in fact, if I change this to a and make a slider, whatever I pick for my a value, that generates the top part of the circle. Now the bottom part of the circle is generated by taking the negative of that. So this will be, I'm going to type a in here again so that you can see this. like that. And so again, as we change A, now we've got our circle. One equation has to define the bottom, the other equation defines the top. And now the reason for that is because if one equation defined both the top and the bottom, it wouldn't be a function, right? Because it would fail the vertical line test. So we can't have this. We need these two equations to represent these two parts. Okay, now of course, f also can go over here, but I'm restricting my x values to be positive. Okay, so where x is greater than or equals 0. Now that is this graph right here. Now what I'm going to do here is I'm going to cut out part of the curve. So I'm going to come in here and I'm going to cut a piece out so that when I revolve, this piece is no longer there, and I'm only interested in revolving this around the axis. And what that does, if we go back to the animation, making the r value, changing the r value, that, as you see, as I move the r, that cuts the hole in the center. So it's going to change the size of the hole in the center. Okay, see it's right in there. Okay, so this guy's going to get revolved around. Now what we need to do is we need to come up with an equation for it. And so to find this, we need the shell. And so we know that for the pieces of the shell, we have the following. Okay, so let's take a random chunk in here. So this guy's going to get rotated around, right? And so if I take this guy right here in the blue, and I draw it sideways, okay, I'll draw it up and down, I'll draw it vertically if I can. Okay, so what I've got here is I've got the shell that's gonna wrap around and it's generated by this. So let's discuss a piece of the shell. So if I take the shell, the best way to do these problems, guys, is to think them through just like this and make sure that you're getting all of the information. I would advise you to not try to memorize formulas and just try to draw these pictures out on your own. I think you'll be more successful that way, especially if you go on to other math classes, particularly Cal 3, where you're working a lot with three-dimensional objects. So, what do we have here? Well, I know that this random guy here, is out some distance x. Okay, I don't know where x is. I just know that x falls between little r, the little radius. Little radius is this distance right here. And I know x falls between that and the big radius, big R, there, okay? But I don't know where x is, so x is somewhere out there, it's random, okay? So the distance out here, the radius of this guy, okay, this is infinitely thin, okay? So the radius out is going to be whatever we'll call it x, okay? So x, and it's some specific x, so let me call it x star. And so we know that if I take and I unwrap this thing, this length right here is the circumference. So the circumference is equal to 2 pi times the radius, and x star is the radius. Now, what's the height of this guy? Well, the height is the difference between f and g. So the height of this is f of x minus g of x. Well, if I take f of x and subtract g of x, I'll do that over here as a side note. F of x minus g of x is the square root of big R squared minus x squared minus, okay, this minus this guy. Well, these guys are the same, and really the negative and negative make it positive. So what do I end up with? I end up with 2r squared minus x squared. So this right here is this length, okay? So I'm going to write that in here. So it's 2 square roots of r squared, big R squared minus x squared. Now what is the length, the base length here? That's the other piece we need. So the base length, guys, is this little length right here, which is this tiny length right here, which we call delta x. So the volume of just this sphere right here, the volume of just this guy, as a function of x, so regardless of where x is, and you can go ahead and play around with the different x values. The volume as a function of, well, I shouldn't even say as a function of x because it's going to be changing, but I'll say the volume is given by taking this length by this length by this little length over here, which is delta x. Okay, so what's that going to be? Well, that's going to be 2 times pi times x star. Now this right here is also x star because that's how far over we came. So that's this and this, how far over we came. So that'll be, essentially it is f at x star minus g at x star, and then times delta x. So we could simplify this. Well, we could at least plug this in and get this. So this would be 2 times the square root of large R squared minus x star squared delta x, like that. Okay. Now what we want to do is, we've got a whole bunch of these cylinders, okay, that are being stuck in here. There's a little cylinder here, another one here, another one here. Okay, they're all over the place. So what we want to do, let me get a little bit more room here. Okay, what we want to do is we want to add up all of the cylinders from, now where to where? Well, the cylinders start here and they end here. So our x values travel between little r and big R, like that. Okay. And so this is going to be this 2 pi I'm going to pull out because it's just a constant coefficient here. I don't need it in there. This was a specific x, but now we're going to let x vary between little r and big R, so we'll just call it x. Okay. And then times 2, we're going to pull this 2 out in a second, big R squared minus x squared. Now, this delta x is becoming super small, so we're going to denote it as dx, like that. So let's pull a 2 out here. So this could be 4 pi little r to big R, okay, of x times the square root of r squared minus x squared dx. So now what we need to do is a substitution, because we need to find an antiderivative for this. So we're going to sub in u, which we're going to let equal r squared minus x squared. Now we're going to need du and dx, so du is equal to negative 2x dx. Don't worry about this r. Big R is fixed. It's not varying, okay? Only x is the guy moving around here. So when we take the derivative of this guy, the derivative of this is 0 because it's a constant. Okay, so we get this. Now, what we can do is we can replace, this, what dx is equal to, in here. So what I've got is du over negative 2x is equal to dx, which means that this is going to be 4 pi times the integral from little r to big R, x square root of u, and dx is equal to this guy right here. So that'll be du over negative 2x. What you'll notice is that this x and this x cancel. And they can cancel here because x is not 0. If x were 0, here, right at this spot, then this guy falls apart. Okay. So what else have I got? Well, the negative 2 and the 4 are going to cancel to give me a negative 2 pi on the outside, right? Because 4 divided by negative 2 is negative 2. So this is going to be negative 2 pi between r, little r and large r, square root of u du. Now I can take the antiderivative of this. And so the antiderivative of the square root of u, let's write it as u to the 1/2. Okay, so we take the antiderivative, we add, whoops, I don't want y, I want u. We add 1 to 1/2, which gives us 3/2, and then we divide by 3/2, which is 2u to the 3/2 over 3, like that. So that's the antiderivative here. So let's go ahead and put that in there. So this would be negative 2 pi times. Now, I didn't switch, and I probably should have here. I usually end up waiting to the end. My bounds for my integration. So when you do a u sub, you should switch these guys, right? Okay, so let's go ahead and switch those guys over here. Well, I'll switch them right here. If x, so remember these guys were what x rotated between. So x varied between little r and big R. So if x is little r, then what is u? Well, then u is big R squared minus little r squared, because x is little r. So our lower bound for our integration, this guy dealing with u, okay, this guy should get replaced with big R squared minus little r squared. Now what about this guy up top? Well, if x is big R, then u becomes big R squared minus big R squared, which is 0. So this guy becomes 0. So my bounds, let me write it in terms of the bounds. Okay. So what I should do is I should really write this out like this. Big R squared minus little r squared, 0 on the top, square root of u du. And we know, because we did I did the workout for the, I did it up here, for the antiderivative, we know that this is negative 2 pi times 2u to the 3/2 over 3 evaluated between r squared, big R squared minus little r squared, and 0. So we plug in 0 first. And so when I plug in 0 first, I get negative 2 pi times 2 times 0 to the 3/2 over 3. And then we're going to subtract, I'll just do it like this, then we'll subtract this guy plugged into here, which is 2 times r squared minus little r squared, like this, to the 3/2 over 3. Now this is 0, right? And so when I multiply this in, negative 2 pi times a negative is going to become positive. So this will be, the back end will be equal to 2 pi times 2 times big R squared minus little r squared to the 3/2 over 3, which will be 4 pi, times big R squared minus little r squared to the 3/2 over 3. And so this right here is the formula. If you tell me what you want the large radius to be and the small radius to be, I plug it in here and I tell you the formula for the volume of the sphere. So I can tell you, if you give me a number here and a number here, I can tell you how much volume will be in this object that you see over here that's been revolved around, this guy right here. Okay? If we go down to the solution, sure enough, they've got the same exact thing, right? Okay. I'll do one more video on revolving about other lines, and then I'll let you have at your homework.